Now that we have explored some differential equations, we're going to move on to study the solutions to them, and in particular, solving the two different types of linear differential equations that we have seen, as well as developing numerical solutions or approximations for the equations that we do not have exact solutions for. Let's first of all start by reviewing the simplest differential equation that we've already studied and the solution to it that we have already seen. So again, this equation states that the rate of change of a function is proportional to the function itself, and it has a unique solution that the function that satisfies this equation is in fact the exponential function. How about other types of differential equations? The first thing we can do is the simplest, and that is to check whether a given function satisfies a given equation. So that means, again, thinking about, for example, how if I ask, does x equals 2 satisfy the equation x squared equals 4, I would simply be plugging it in and seeing whether or not the equality holds. Similar to this here, the solution to a differential equation is a function, and it is in fact a solution if the equality in the differential equation holds. Differential equation is an equation that involves a derivative, so the first thing I can do is take a derivative of this expression and then check whether or not it satisfies this rule. So let's take a derivative of our y here. So I have that y prime, and then this case, or in this case here, the function is quite complex, so we're going to have to think about the chain rule as applied to this function. Outside function is my degree. It will come down to the front, and the power will get reduced by 1. 1/2 minus 1 is -1/2. And then I have to follow up by the derivative of the inside, which in this case is simply 2. Now, I can see that I can actually simplify this derivative by, for example, canceling out the two 2's. And I can even then make it a little more easy to digest sort of on the eyes if we bring the negative power down to the denominator. So this is the same as 1 over 2t plus 1 to power 1/2. Now the idea is, let's say I've simplified it, is this the same as the differential equation given, or is this similar, or is this definitely not satisfied? So in my differential equation, I have that y prime is equal to 1 over y, whatever y happens to be. And once I took the derivative, I can see that y prime is equal to 1 over 2t plus 1 to power 1/2, which is in fact y. So this is indeed 1 over y, and then I can clearly see the same differential equation as I have above. So this function does satisfy this differential equation. For the next one, we're asked to check whether a negative exponential function satisfies differential equation y prime equals 1 minus y. So again, I'm simply going to first of all take a derivative of this function. Notice that I move freely between the notation dy by dt and y prime as long as the independent variable with which I'm taking the derivative with respect to is understood. So for this one, the derivative is, I'm going to leave y not alone because that's a constant. The derivative of e to the negative t is simply itself. And then I have to multiply by the derivative of the inside, which in this case is minus t. So the derivative of that is minus 1, and I can put that in front of my entire function for to simplify this a little bit. Now, what does that actually tell me? This expression I've already seen before. This is the same as this expression here, which is equal to y. So what I have in this case is that y prime is actually equal to minus y. Again, that is because this entire expression is simply y, as we can see here, and then I have an extra minus in front. We're asked whether or not this function is a solution to this equation, and this equation states that y prime needs to be equal to 1 minus y. Well, clearly, minus y is not the same as 1 minus y, which means that this particular function is not a solution to this particular differential equation. So again, checking whether something is a solution or not is simply figuring out the derivative of this and seeing if the derivative in fact satisfies the equality given in the differential equation. Making up differential equations is actually a bit easier because you get to decide on the relationship that is to be satisfied. So let's see here, we have 3 different examples. We'll start off with, we would like the function y equals x squared to satisfy some kind of differential equation. Well, I can simply take a derivative of it, and I will have y prime equals 2x, and there you go. This is the differential equation that is satisfied by this function. So this is a solution. Now there may be other solutions, but this is most definitely one of them. I can even take the second derivative, and then I will have what we call second order differential equation that involves higher order derivative. So in this case, y prime is equal to 2. And again, I am guaranteed that this function satisfies this differential equation because I derived it from the function itself. Let's see what we can do in terms of differential equations for y equals e to the x. So for example, y prime is equal to e to the x. This function is, the derivative of it is itself. So I can actually rewrite this even simpler because e to the x is just y itself. This differential equation can be written as y prime equals y. And in fact, because any derivative, second, third, fourth, and so on, of e to the x is just itself, it is a solution to lots of really simple-looking differential equations, such as y double prime is equal to y, y triple prime is equal to y, and whatnot. See if you can do this for sine of x in terms of the differential equation that involves y prime and differential equation that involves y double prime. The other types of questions we can ask are of this particular kind. Find the value of a constant a so that a given function y equals e to minus x is a solution to the given differential equation y double prime minus ay prime is equal to 0. So here, the approach is exactly the same. If I would like this function to be the solution to this particular equation, it means that when I plug it in, the equality actually has to hold. Now, this equation involves y double prime and y prime, so first I have to calculate those. If I start off with y equals e to the negative x, then y prime is minus e to the negative x because of the chain rule, and y double prime is going to be e to the negative x again, because I'll be taking the derivative of this, and then the chain rule will give me a derivative of the inside, which is one more time going to give me the negative in the front. So what I'm going to do now is take all this information and plug it in to the differential equation that's given. Y double prime is then, as given in my little table, y double prime is e to the minus x. So I'm going to have e to the minus x minus a times y prime, which is negative e to the negative x. And according to my equation, this whole thing has to be equal to 0. Let's see if I can simplify this. I'm asked for what values of a does this actually hold, so I'm trying to find all possible values of a that will make this equation true. If I open up the brackets here, I'm going to get e to the negative x, and then I see that the two minuses will cancel each other out, and I'm going to get plus a e to the negative x. I can factor out e to the negative x, and I'm going to have 1 plus a in the bracket left. This is a nice looking equation because I now have a product of two things that is equal to 0. A product is only ever equal to 0 if one of the two things equals to 0. So I can break this equation into two pieces. Either e to the negative x is equal to 0 or 1 plus a is equal to 0. Well, let's attack them one at a time. E to the negative x is equal to 0. That can never happen. An exponential can never be equal to 0 or go below it, so this part produces no solutions. Whereas 1 plus a equals to 0 when a is equal to negative 1, and that is going to be my only possible value of a which will give me that this function satisfies this particular differential equation. Now, it is one thing to check whether a given function is a solution to a given differential equation. What we've done before in the last couple of slides is just plug it in and see whether equation holds or not. It is a whole other thing to actually finding a solution to the equation we've never seen before. So we're going to start with a fairly simple form here. dy by dt, or y prime, is equal to 1 minus y. What we're going to do is introduce a new variable z to replace the entire right-hand side. Okay, so let's call this z and then see whether that helps us in any way. It's nice that the right-hand side is now one small variable, one concise variable. However, the problem now is that the left-hand side talks about the derivative of y, while the right-hand side talks about some new function z. So we would like to consolidate the two and have a differential equation involving only one variable, preferably our new variable z. So what we're going to do is forget that this is here for a second, and let's just focus on the fact that z is equal to 1 minus y. What is z prime then equal to, or dz by dt? So I'm going to take this equation and then take a derivative of it with respect to time. The derivative of 1 is just 0. The derivative of minus y, recalling our implicit differentiation or simply the chain rule, you notice that the derivative of y is in fact just a derivative of y. We know it depends on t, so it will just be minus, which got inherited from here, dy by dt. Now, in this expression, I would like to replace dy by dt, so I'm going to work with this for just a little bit longer and rewrite this for dy by dt, not dz by dt. From this expression here, dy by dt, if I simply multiply both sides by negative, I will get exactly what I'm after, and I can see that dy by dt is in fact equal to minus dz by dt. I am now going to use this expression to consolidate my two variables here. So what I have is that dy by dt, which is the left-hand side here, is actually the same as minus dz by dt. So I'm simply going to replace it with that. The left-hand side here is minus dz by dt, and the right-hand side here is exactly what I called z. So this one simply gets transferred down as z. Now, was this whole thing worth the trouble? Well, let's take a look what we have here now. We've managed to transform dy by dt equals to 1 minus y into the equation that says minus dz by dt is equal to z. Or, if I would like to rewrite it for dz by dt, I'm going to have that dz by dt is simply minus z. Why is this so much better? Well, it's that much better because this is the equation of the form we have seen before. This is exactly the equation of the form y prime is equal to ky, where y is now just called z and k is equal to -1. So this equation I can solve. We've managed to transform an equation we did not have a solution for into the equation that we can in fact solve. We can solve this one. And recalling how this all works out, what we have here is that z, the solution, is some z naught, an initial condition, e to the power of the constant, which here is simply -1, times t. So z naught e to the power -t. Now, we started with the equation for y, so we would like to have a solution in terms of the original variable, which was y. So now that I have a solution in terms of z, I simply have to rework it back in terms of y. So I'm going to be replacing my z's with 1 minus y's everywhere I see them. So what am I going to have? On the left-hand side, I'm going to have 1 minus y is equal to z naught, which is going to be 1 minus y naught, e to the power -t. Now, it would be nice if I had this in terms of y equals stuff, not 1 minus y equals stuff. So let me rewrite that as that. So moving things around, I'm going to have that y is equal to 1 minus y naught e to the power negative t. And that's it. This is my solution to this original differential equation. Notice that we can actually generalize this process for any constants here. In this equation, I have essentially one here and one there, but nothing in the process was really attached to what the numbers are. So we can derive a more general solution to a more general differential equation. Here I have a and b instead of 1 and 1 as before, and here they're taken into account in the solution. So this is the second type of differential equation whose solution we're going to consider, and this is its solution. Let's practice for a couple of examples here how we can actually work this out. This is really basically a matching game. You're matching the differential equation to the one you're given, and you're going to produce the solution with the constants you're now handed. So here I have that dy by dt is 3 minus 2y. To make it easier to go through, you can, for the first few, write down the exact same differential equation on top just to see really what the a and the b are. And here I notice that my a is 3 and my b is 2. The one thing to be careful with is that this minus is built into the formula. So if you have a minus in your equation, this is the minus that's given, and b is actually the number in front of y. Once you have your a and b, you can simply plug them into the general formula for the solution to produce the general looking solution. So what I'm going to have here is y equals a over b, or in my case 3 over 2, minus brackets a over b, which once again is 3 over 2, minus y naught, so that's an initial condition, and in this case we're actually given that y naught is 0, times e to the power of negative bt. Again, keep in mind that b is the value that is directly in front of y, with minus being actually part of the equation. So my b here is 2, so I'm going to have e to the power negative 2t. Now, of course, I can simplify this a little bit by getting rid of this 0. So overall, I have 3 halves minus 3 halves e to the negative 2t. I can check whether or not this is in fact a solution to this equation by taking a derivative of this and seeing if it satisfies this particular equation. And I encourage you to do so for extra practice, how to actually, first of all, check the solutions to differential equations and how to take derivatives of exponential functions. This is really great practice for that. Let's take a look at this next one. So I have y prime is equal to 3 plus 2y. So again, for the first few, before you get a hang of it, I recommend that you write the general form on top of it just to see what the a and the b are, because here it makes it very clear that a is 3, but b now has to be minus 2, because the general form has a minus inside of it. So a is 3 still, but b is now negative 2. And this will, of course, affect how you plug them into the formula. So in terms of the solution, I'm now going to have minus 3 halves minus negative 3 halves minus y naught. And again, hopefully that's something that's given to us, and it is here. So y naught is 1. So I'm going to have minus 1 e to the power negative bt. So b is minus 2. Negative of that is 2, so I'm going to have e to the power of 2t. And once again, of course, I can pull together the two terms inside the brackets here. So I'm going to have minus 3 halves minus 3 halves minus 1 is negative 5 over 2. With the negative in front is going to become a positive. So I have plus 5 over 2 e to the power of 2t. And again, I strongly encourage you to actually check whether or not this is true. So in both cases, take a derivative of this and make sure that that derivative satisfies this equation. In summary, what we have so far developed are two different solutions to two different differential equations. The first one was easy, so let's think about the formula and how this is represented on the graph. If I have this equation, dy by dt is equal to ky, or y prime is equal to ky, the solutions are going to be a family of curves, y equals y naught, the initial condition, e to the power of kt. So the curves will depend, their actual shape will depend both on the value of k, whether it's positive or negative, and the value of y naught. But we can sketch the general shapes and what they will look like. So for example, if I have positive y naught corresponds to, of course, the initial condition, so it will correspond to the y-intercept here. If I have a positive y naught and I have a positive value for k, then I'm in the case of exponential growth, and the solution curve will look like this. So this corresponds to y naught is positive and k is positive as well, which indicates growth. If y naught is positive, so let's say it's still this number, but k is negative, this will correspond to the exponential decay, because then the curve will look like this. So y naught is still positive, but k is negative, which will then represent the decay, right? E to the negative power will be a decreasing curve. The cases for y naught being negative will lie in the third and fourth quadrant when y naught is down here, and these are generally not going to be the cases we're interested in for applications, because no applications really have that the initial condition is some negative value when we're talking about things like population growth, radioactive decay, the spread of disease, and whatnot. This is the first type of the differential equation we've seen. The second one that we've just developed the solutions for in this lecture was this other linear type. So not only do we have a proportionality constant, we also have a fixed constant term. So the other way to rewrite this would be a prime is equal to a minus by, and we have just derived that the solutions to this equation were curves of the form a over b minus y naught e to the power of negative bt. Now let's take a look at this entire expression a little bit closer. There are a lot of constants, and so it's going to be hard to analyze in its entirety. But what we can notice is that the solution form will really depend on this exponential term, and in particular, what is happening in front of it. So the initial condition is something that is generally either given to me or we get to pick for analysis. What if y naught, this is going to be our first case that we're considering, what if y naught is actually equal to a over b? If I have that this term is equal to this one, then this entire bracket is going to be 0. 0 times anything is just 0. So this whole thing is gone, and I simply have that y is equal to a over b. It doesn't change, it always stays at a over b. This is what we call a steady state. If we were to graph it, this would be a particularly boring graph. A over b, the function will always stay there. Now, what about other cases? If we're interested in the case of equality, then we're probably interested in the cases on either side of equality. So either when y naught is bigger than a over b, or when y naught is smaller than a over b. Will this produce qualitatively different behavior? Let us see. First of all, the other thing that we have to think about is what happens to the exponent here. Is b positive or negative? So is my exponential actually decreasing like in the decay or increasing like in the exponential growth? And for the purpose of this analysis, I'm actually going to restrict ourselves to b being greater than 0, because this is where most of the applications are going to lie, with the equations that have the actual minus built in and b being positive here. If b is positive, let's think about what happens in both of these cases as t goes to infinity? So let me analyze this as t goes to infinity. In the long term, what happens to the population, or what happens in the disease spread as time goes on? If t goes to infinity and b is legitimately positive, then what I have in the power here is a negative number. E to the negative power, as the power goes off to infinity, approaches 0. So this term approaches 0. And then it doesn't matter what I multiply it by, the whole thing approaches 0, and y will once again approach a over b. Now, where the two cases will actually make a difference is when we're considering t approaching negative infinity. Then in one case, we're going to approach negative infinity, and in the other case, we're going to approach the positive infinity. However, again, in applications, t approaching positive infinity makes sense, but not so much when it approaches negative infinity. What we're going to do here is stick to our analysis of these two cases and draw two graphs as to how we can represent both of them graphically here. So as time goes on, y approaches a over b, which means that this is the horizontal asymptote here. So I can label this on my graph and sketch a little horizontal asymptote, and then think about what the curve will look like near it. If y is bigger than a over b, it means that my starting point is above the horizontal asymptote, but in the long term, my curve approaches the horizontal asymptote. If y naught is less than a over b, that means that I'm starting below the horizontal asymptote, but again, as the end behavior, approach the horizontal asymptote. So these are generally going to be my two cases. I can start at the steady state and then stay there forever, or I can approach it either from above or below in a continuous type of manner. We now have two differential equations that we can solve exactly. The first one is y prime equals ky, whose solutions are fairly straightforward and correspond to either unbounded growth or decay all the way down to 0. The second one, of the form y prime equals a minus by, corresponds to the growth or decay that has a horizontal asymptote that can be calculated out of the coefficients of the differential equation itself. We're going to see a couple of applications and how to apply our general formulas to particular cases. The first one is the organismal growth problem that we have seen previously. So let us remind ourselves that we stated that the mass of the cell is equal to density, which is a constant, times volume, which in the case of cubic cell is simply length of the side cubed. From here, we derived the formula for the rate of change of mass as 3dl squared times dl by dt, and we actually said that this 3 will get absorbed into the density constant, so we can simply have it as d here. Later, we also approached this derivation of this formula from a different angle, talking about how the cell ingests food at the rate proportional with the proportionality constant s to the surface area, and it consumes food at the rate proportional to the volume, so VL cubed. Now, when we are talking about the change of mass, we can think of that as absorption minus consumption. So what we have is SL squared minus VL cubed. But on the other hand, this is the same as what we derived using a different approach, so these two must be equal. Again, let me pause here for a second and remind you that the surface area of the cube, of course, is 6 little faces, but I am omitting 6 here because it can get absorbed in the proportionality constant s, the same way that 3 here can get absorbed into the density constant d. Okay, so the numbers get absorbed into the actual letter constants here. Now, setting these two equal, we can solve for dl by dt, and what we end up getting is, let me write this out slower. So SL squared minus VL cubed, which is the right-hand side here, and we will divide both sides by DL squared. So all over DL squared. And then after we have split up this fraction and canceled out the L's, we're going to get S over D minus V over DL, which we can rewrite in terms of constants, or we can simply sort of stand back a little bit and look at this equation carefully. What I have here is the derivative of L is equal to some constant minus some other constant times L. This is exactly of the form y prime equals to a minus by. So the great news is that before, this was the equation we did not know the solution to, but now we can, in fact, solve it. Now, I'm not going to write out the general solution formula for this particular application, but I encourage you for practice. What I will point out, however, that is important is that recall from the last slide, when we analyzed equations of this form, we have noticed that their solutions have either a steady state at a over b or horizontal asymptote at a over b. So a over b is a number of interest. In this case, this corresponds to the horizontal asymptote of the solution as a over b. My a is s over d, my b is v over d. So we have s over d divided by v over d, or in the simplified form, s over v. That means that in my solution, I'm going to go from the derivative of L to L itself, and L itself as a horizontal asymptote will approach S over V. So as the cell grows, these constraints of the ingestion and the consumption of nutrients will lead to the length of the side of the cube of the cell, so the dimension of the cell to be bounded by this ratio S over V. So the ratio of the proportionality of the surface area to the proportionality of the volume. These two constants are what decide the limiting size of the cell that it can possibly approach as it grows. Let's take a look at another application, the von-Bertalanffy equation, named after Ludwig von Bertalanffy, an Austrian biologist known for his work in biology as well as information theory. He is one of the founders of the general systems theory and is actually well known for this equation as the mathematical model of an organism's individual growth. So what we notice here is that this equation looks slightly different from the ones that we have seen before, but maybe it's just the exact same form disguised as something else. So if we are to solve it, let's try to massage it a little bit to see if it's of a familiar form. So what I have here is dl by dt, where L corresponds to some kind of a dimension generally of an animal. If it's a spherical cell, this L will be the dimension that is the radius. If it is a cubic cell, this will be the size of the length, the side length. So what I have here is, notice that I have a K, a constant of growth. I have an L, which is the same as my dimension here, and I also have L infinity. This is what is called asymptotic length, and this is also a constant. Now, the reason it's called asymptotic length is going to become apparent later in the analysis. For now, we're simply treating this as a number. So what I'm going to do is open up the brackets and multiply Kn. So we have KL infinity minus KL. So here it's a constant times a constant, here it's a constant times my variable L. So this makes it very clear that this equation in fact is of the form A minus BY, because this is a constant, can be modeled by A, and this is a constant that can be modeled with B. This means that I can solve this equation. So let's write out the general solution. Recall that the general solution will be A over B, so in this case, KL infinity over K. Let's write this out in full detail. Minus A over B again, KL infinity over K, minus the initial condition. Here we're told that L naught is 0. So for example, in terms of length, a cell starts at some trivial dimension. So minus 0 e to the power of minus b, which is k, t. It's going to take a few times before you really get a hang of going from the general form in terms of AB to the constants, so do practice this a little bit. Now, I'm going to simplify this equation as best I can. So first of all, I notice that minus 0 I can simply ignore, and I can also notice that in all of these terms, k's will cancel. So in the end, my equation is actually going to look quite simple. It's going to be L infinity minus L infinity e to the minus kt. As already pointed out previously, a over b is an interesting quantity when it comes to these models because it describes the horizontal asymptote. And here I can see that a over b, in fact, turns out to be equal to simply L infinity. So L infinity is my horizontal asymptote for this model. There's another way to derive it simply from the equation itself, and that is to look at this equation and think of what happens as time goes off to infinity. So as t goes to infinity, this power becomes a very large negative number, minus infinity. E to the negative infinity tends towards 0, which means that this entire term tends towards 0, and all I have left is that L tends to L infinity. If we are to sketch this now as a graph, again, I'm only interested really in the positive values for t. I notice that my L infinity here is then my horizontal asymptote. In this case, it's known as L infinity. In the previous slide, it was also known as A over B. So I have this as a horizontal asymptote for my model, and my initial condition says I'm going to start at 0. Now I'm going to make an assumption that this is going to be a nice continuous curve, so it's going to approach a horizontal asymptote in some kind of continuous manner. Now I don't actually know whether it's a curve that looks like this or maybe a curve that looks like this. I'm just going to draw a general shape simply indicating two important pieces of information. It starts off at 0 and it ends up approaching or plateauing at L infinity. As I mentioned, this model is used for description of various animal individual growths, and in particular, this is one of the models that is used to describe fish length growth. Now, different species of fish, of course, will grow differently depending on their genetic makeup, and this is what the constants k and L infinity will actually help determine. But the general growth model is the same for many of the species. Let's just take a second here and really compare this form of the equation with the form that we have originally derived our solution for. Both of them have their advantages and disadvantages. The original form has the advantage that it's easily seen to be a constant minus a proportionality constant times the original variable, but this form has the advantage, after k has been factored out, of seeing the horizontal asymptote immediately. Both of these equations are completely analogous in terms of what solution corresponds to them. They're simply written out differently to highlight different pieces of information. This shows that it's a linear model. This shows the horizontal asymptote explicitly. Another application where we see the now familiar differential equation is Newton's law of cooling. So let's start from the beginning as how Newton's law of cooling is actually stated and what that means for our solutions. The way it's stated says the rate of change of temperature, so this immediately suggests the derivative if we are to write it out. The rate of change of temperature is proportional with some proportionality constant k to the difference between the temperature of the object itself and the ambient temperature. So what we have is it's proportional to the difference, and it can go either way. The ambient temperature minus the temperature of the object, or it could be the temperature of the object minus the ambient temperature itself. Because the law of cooling is generally stated as the law of cooling and not the law of heating, we are mostly going to work with the first form, but the second form is completely analogous. It's simply going to depend on whether you want your K to be positive in one case or negative in the other. Again, because the law is stated as a law of cooling, it is the cooling case where we consider K to be positive, because the temperature of the object is going to be cooling down to the temperature of the ambient environment. If the object is heating up, in our model, this will correspond to K being negative. So we have here the same exact setup we have just seen with the von Bertalanffy model, where I have a constant K, another constant E, and then my actual object's temperature. So I can open up the brackets and rewrite it to see the A minus by form, or based on our previous analysis here, we know that this constant up in front actually corresponds to the asymptotic or the plateau length. So this here will correspond to the temperature that will eventually be reached by the object. And here we have, both intuitively and really from the mathematics we've just seen, the two cases. It can be heating up or it could be cooling down. So let's sketch two quick graphs of both of those scenarios. So if my object is cooling down, that means that it is starting at some initial temperature T0 that is above the eventual ambient temperature, and its temperature is reaching the ambient temperature slowly this way. If my object is heating up, that means that it's starting at the temperature that is below the ambient temperature E and is reaching that temperature slowly. So the two scenarios, for example, that we think about all the time is cooling down, the ambient temperature is the room temperature, and the object we're talking about is, for example, a cake being taken out of the oven. Heating up, we're thinking of the ambient temperature still being room temperature, but the object is, for example, ice that has been taken out of the cooler. Now again, because this is the form that we are familiar with, we can actually find the exact solution to the equation. So instead of talking about the rate of change of temperature, derive a formula for the temperature itself. Let's see how we can do it. We can actually do it in a number of different ways. We can do it from scratch, or we can do it from using the formula. Normally, once we've derived the formula, we will always use the formula, but I will take this opportunity to just practice the from scratch technique one more time to show you the actual algebra behind it. So my equation is T prime, from the previous slide, dt by dt is K E minus T. And what I'm going to do, if you recall, is I'm going to want to rewrite this fully in terms of one variable that I'm going to call Z. So here, Z is equal to E minus T, and then I'm going to take a derivative of this equation. So Z prime ends up being what? The derivative of E, which is a constant, is 0, and the derivative of T is simply T prime. So this is Z prime equals negative T prime. I'm now going to plug all of this back into my equation, and what do I get? T prime is then negative Z prime equals to, and on the right-hand side I have K times Z. I can multiply both sides by -1, and I end up with the equation that I definitely know the simple solution for. This is of the form y prime equals ky, except for, of course, y is being called z, and there's a negative in front of it. So the solution to this is going to be z equals to some initial value z naught e to power minus kt. Once I have a solution in terms of z, I would like to bring it back to the solution in terms of my original variable, which is t, and I'm going to use this relationship between the two variables to rewrite my current solution in terms of t. So z on the left-hand side is simply e minus t. Z naught is going to be e minus t naught, and I have e to the power of minus kt. If I now take a minute to rewrite the whole thing for t, because this is the temperature that I'm after, I'm going to move e to the right-hand side and then multiply everything by -1 to get rid of this negative. I'm going to get that T is equal to E plus E minus T naught, e to the power of minus KT. And this is likely the form that you have seen the Newton's law of cooling presented in Calculus 1 courses. The temperature of the object has this relationship to the ambient temperature and some kind of cooling down constant K. Again, this is the way to solve it completely from scratch, but we really don't have to do this once we have derived the general formula. We can massage this equation in the same way that we've done with von Bertalanffy model to match what we already know. So from the formula, from y prime, let's be a little more precise. From this formula, what do we have? So my original equation is of this form, so let me rewrite that. T prime is equal to K E minus T, which doesn't quite match the A minus BY form, but in order for me to do that, all I have to do is simply open up the brackets here. So what I have is T prime is KE minus KT, and now I can notice that this will act as A and this will act as B, therefore producing the solution of A over B, so KE over K minus A over B one more time, so KE minus over K minus the initial condition T naught, which in this case we cannot assume to be 0. We have not been told to assume anything like that, e to the power of minus KT. And as before, let me just cancel things out here and simplify this equation a little bit. So what are we going to have? T is equal to E minus T naught, e to the power minus KT. Okay, and these, I just noticed I made a small typo here. There we go, minus. And this is now the exact same equation as the one derived using the from scratch method. So of course the methods are exactly the same because this general formula was derived exactly through the substitution of Z, and therefore the answers should be the same. Now once we have the general formula, we can use it to our advantage in a variety of applications, in particular any applications that involve cooling down and heating up objects that call for Newton's law of cooling.